Our Chapter 9 remote learning series for the GLB. Today we will be talking about hydrolysis reactions of salts. So basically those salts that we make from the acid-base reactions, what's happening with them in water, and how that relates to this concept of buffers and what buffers are. So a salt that we know, right, we know that a salt consists of a cation and an anion. The cation usually comes from a base, and the anion is coming from the acid, right? When we have an acid-base reaction, we know that we're going to produce a salt and water, and sometimes some CO2 or H2 as well. But the salt that we form, the cation comes from the base, and the anion comes from the acid. So you could always work backwards to figure out which acids and bases you had, or potential acids and bases you had, based off the salt that is produced. So when we think about that cation of a base is the conjugate acid of the base from which it was formed. If you need to go back and review what a conjugate acid and base are, please do so. The anion of an acid is the conjugate base from the acid from which it was formed. Now the strength of the conjugate acid or base will depend on the strength of the acid or base that they came from. When an acid is strong, its conjugate base is weak. When the base is strong, the conjugate acid is weak. And the reverse would be true as well. So the pH of a water solution of salt depends on the strength of the salt cation as an acid that it comes from. So when we're talking about this, we're talking about the concept of what happens to this salt when I put it in water, right? We are saying up until now, we haven't really thought about this, but when I have NaCl, we could say NaCl, the salt, right, table salt, came from an acid-base reaction. And that when I add table salt to water, what happens to the pH of that water? Does that affect it? And so we're going to look at this, right? So a solution containing, I guess we could be very appropriate here and say dissociated salt, NaCl, has the same pH as the water that was used as the solvent for the solution. So the Na plus ion is the conjugate acid of the strong base NaOH. And is a very weak acid. So Na plus is a very weak acid because it came from a strong base. Cl minus came from the conjugate base of the strong acid HCl, which means that Cl minus is a very weak base. So we have a very weak acid and a very weak base being put into water. So neither the Ca plus cation or the Cl minus anion would react a whole bunch to produce extra amounts of OH minus or H plus. And this is why when we add NaCl to H2O to water and make a solution, a saltwater solution, we don't really see a significant change in the pH. However, that's not always the case. Let's look at example, a solution where we use the salt sodium carbonate. So now we have this salt. The pH of this solution is drastically higher than that of the water used for the solution. So we make a very basic solution when we dissociate this salt in water. So let's think about this. Na plus we know comes from things like NaOH, which means it has to be a strong, NaOH would be a strong base, which means Na plus is a weak acid. So we have a weak acid in our solution. But then let's look at the CO3 minus 2. This is the conjugate base of a weak acid, HCO3. And HCO3 is a weak acid, which means that CO3 minus 2 is going to be a much stronger base, the conjugate base. So we're going to have a stronger base here, plus water, giving us HCO3 plus, right, which would be the weak acid. This is the base, this is the conjugate acid, this is the acid, this is the conjugate base. So we're producing OH minus in this case when we look at this. And when that happens, we know we're going to have more OH minus in the solution than we did if it was just pure water, which means that the OH minus concentration would go up, which means our pH of our solution would go up, and the solution would be more basic. So some rules to kind of help think about this pH of water solutions. Salts containing an anion of a weak acid and the cation of a strong base will form alkaline, or what we would call a basic solution. salts containing the anion of a strong acid and the cation of a weak base will make acidic solutions. Salts containing anion and cation from equal strength acids and bases will be neutral. So if they're both strong or they're both weak, it will be neutral because they will cancel each other out. So here's just an example. This is water, pure water, and then sodium acetate in water solution. And we've added an indicator that will turn pink when a base is formed. So basically we can see that the pure water doesn't go basic because the pH would be neutral at 7. But when we added sodium acetate to the water, we end up with a basic solution. And this is because that acetate ion, the CHCO3 right here, this guy, the acetate ion, comes from a weak acid. So it's going to form a very strong base, which in water would produce a lot of OH-. So these strong acid, weak base, weak conjugate bases, and these strong bases, weak conjugate acid pairs are very, very important, especially in physiological situations when we're dealing with buffers. So in a human body, we have a lot of buffer systems that allow our bodies to function the way they do, even when outside influences come in. So, solutions with an ability to resist pH change when acids or bases are added to them are called buffers. Many useful buffers contain a solution or a mixture of the weak acid and a salt of that acid. Okay, so we could look at something like acetic acid and sodium acetate, which we have here. Sodium acetate, the sodium isn't the important part here because remember sodium acetate would dissociate in water. So really what we're looking at is acetic acid and acetate. So here's our acetate and here's the H plus from the acetic acid, right? So we're doing a very like bare bones a very bare bones equation here. When we add any extra acid, so here's our situation, right? Here's our buffer solution. It's going back and forth between being the acid and the H plus and the acetate ion, right? So what will end up happening is if I added more acid, more H plus was added to this situation. So this concentration went up, it would push the reaction to make more of this. If more base was added, it would push the reaction to make more of this. So basically, if we have a higher OH concentration, it will push the reaction to produce these two as products and push the reverse reaction forward. If we add more H+, we're going to push the forward reaction forward. So what we can see happen here is that we have kind of this wiggle room where we can produce one of more or the other, causing the pH to stay about the same. And this is very, very important in terms of physiological conditions. So obviously I have a video posted in our resources section on buffers dealing with the buffer systems within blood and how we have a very tight range of pH that our blood can be in, where if we go too high or too low in our H+ concentration, we can actually start having diseases that can affect things like our organs and things like that. So we have buffer systems in place in our bodies. Here's just an example of that same buffer solution, but if we added extra OH to it. So if we added more base to the solution, what would happen? So a buffer capacity, this is a concept that these buffers aren't infinite. They won't work forever. You could eventually add too much hydrogen plus or too much OH minus, where eventually you've overwhelmed the system and it can no longer buffer. It can no longer hold the capacity, and you will have a sharp increase in your pH or decrease in your pH. So here's just an example to kind of show you what this would look like, right? So a solution on the left is not buffered and the one on the right is. So this is not buffered and this is. We're going to add a universal indicator, which when we add base will go purple and when we add acid will go pink. So we have this buffer solution and a non-buffered solution. So when we add base to both of these, the non-buffered solution becomes basic. However, the buffered solution remains the same. The pH is maintained. If we go ahead and add acid, hydrochloric acid to both of these, right, to fresh samples of both of these, the buffer system still remains the same. It's still able to accommodate and maintain its similar pH, where the non-buffered solution cannot. Lastly is the Henderson-Hasselbalch equation. We won't be using this in tests and quizzes. You will see this show up in your homework, so I just kind of wanted to show it to you and what all the pieces mean. But we won't be going to too much depth with this. But basically, it's for what we will be seeing it will be something where it will be kind of a plug and chug, where if you're given the pH, you might have to find the pKa, or if you're given the pH and the pKa, you might have to find the concentration of the conjugate base, or something like that. HB is just standing for some sort of acid, okay? Some sort of weak acid. So the H goes away and it becomes the conjugate acid, right? So that's what this is representing. In an example, here are some, a table with some pKa's and everything like that. Again, you don't need to memorize any of this. This would all be provided to you. But just an example, you may see a buffer calculation in your homework, and so I wanted to give you an example of what this would look like. So if we need to calculate, if we need to calculate the pH of a buffer solution that contains 0.1 moles of acetic acid and 0.1 moles of sodium acetate, so we have our acetic acid, and the important part here is the acetate. Remember, the sodium's kind of just the cation coming along for the ride. This is the pair for the buffers, the acetic acid and the acetate. So the acetic acid concentration is 0.1, and that its conjugate base, right, and that of its conjugate base, the acetate, is also at 0.1. So the pK for acetate, if we looked it up, is this number here. So what we have going on, this is our B minus on top, right, our conjugate, conjugate base to our weak acid. So our concentration of our CH3COO minus, the acetate ion on top, and the concentration of our acetic acid on the bottom, right? So basically we would plug and chug for the pH of this. The 7.4 came from our resources, our textbook. The log of this divided by this, right? So the log of 1 is 0, so our pH would be 4.74. When the acid and conjugate base concentrations are equal, the pH will always be equal to the pKa. And this is why, because this is the pKa value. And if we have equal amounts of our acid to equal amounts of our base, that means that this number would always end up equaling 1, and the log of 1 is always 0. So it will always only equal the pKa. So again, in terms of just wanting to go through and practice this idea, right, for the following equilibrium, it lies to the what, because blank is the stronger acid. So is it going to lie more to the left-hand side or the right-hand side, because which one of these is a stronger acid? That's the question we're asking. So if you want to take a minute to pause and run through this, you can. We're showing that this is going to lead more to the left because the H3PO4, this guy right here, is the stronger acid, which means this is the weak conjugate base. And again, right, if we have this sodium sulfate will produce a blank solution when dissolved in water because the parent compounds are. So we're asking, is this going to make an acidic or a basic solution? Because the parent compounds, right, if this salt, what are the parents that made this salt? What acid and what base were brought together to make this salt? We'd make an acidic solution because a strong acid and a weak base made these, right? So think about that. The strong acid probably came from H2SO4, and the weak base was probably NH3. We can look at this to determine that was the parents, right, of this salt. And so a strong acid and a weak base means that we're going to have an acidic solution when this salt is dissolved in water. And lastly, which of the following equations best represents how this buffer system would react with the base? So to do this, you would have to identify, okay, if I'm adding base, what would that look like in terms of where the base would be on my reaction, and what would the reactant side look like? So again, when we're adding base, that's OH minus, right? That's where we get our basic portion from. H pluses should have automatically been taken away as not options because this would be adding acid to our situation. So if this reaction asked what would happen if we added acid, we would be looking at possibilities 1 and 3. But because we're talking about adding a base, our only options are to really look at adding, so base would have to be a reactant in here. So now we have to determine, are we talking about having which of these would be a better system of these two for a buffer. And so what we're looking at here is we're saying we have the H2PO4 minus plus some base yielding the HPO4 2 minus, right? So this is our acid, right, donating a hydrogen. This would be the base accepting the hydrogen, producing this and water. The option down here, let's see, does this make any sense? Would we get an HPO4 2 minus giving up another hydrogen and this taking that on? So we want to think about what options we have in terms of what this buffer system would look like. And our best option here would be that we're going to have the H2PO4 acting as our acid, and the H2PO4 minus acting as our acid, and the HPO4 minus 2 on this side acting as the base. This concludes our Chapter 9 slides. Please go ahead, make sure you're reading through the slides as well and not just listening to these videos. It really is important to go through and take the notes. You do need to read your text as well. In our remote learning situation, the textbook is going to become very, very crucial and important. Lastly, you will have homework sets that are up and ready to go. Please make sure you're working on those, and if you do have questions, let me know. Contact me, come to office hours, let's talk, let's make sure that you are set up for success so that you can take the tests and quizzes as they come. So this is actually also the end of our Unit 2. So remember, when we get back from spring break on your exam 2 will go up. And that will be for 5, 6, and 9. So go ahead, look over these. There are slides posted for Chapter 10, which will be on the quiz, but not on the test.